Okay, hello, AB Calc. This is a short lecture on chapter 3.9, differentials. We are going to be working 3.9. Well, we were going to be working 3.9 on Monday the 9th, 9 January. Obviously, school is out because of the snow, but you still have to work the material. This is not a digital learning day assignment. This is your homework for the 9th of January, section 3.9 out of your textbook, differentials. Now, if you did not bring home your differential or you did not bring home your textbook, I scanned in 7 pages from the text, and they're included as a topic dated homework for January 9th. I want to give you a little bit of a lecture per se so that you have some background material. Differentials and tangent line approximation. Notice it talks about tangent line approximations, and that's a big deal in calculus. In fact, if you look at your exam, equation 9 talked about the equation of the tangent line, as did 18, and in fact used the tangent line to find an approximation. So this is stuff that you should already know, but we're going to get a little bit more detail into it. In fact, let me look at this first exam problem that you had. An equation of the tangent line to the graph of y equals the cosine of 2x. Let me go to my calculator and type in y is the cosine of 2x. The standard window zoom 6 is not very useful, but there is a trig window zoom 7 which gives you a nice picture here. So here's the graph of y equals the cosine of 2x, and it talks about the tangent line to the graph at x is pi over 4, and we can actually draw the tangent line on the calculator. It's second program, which is the draw menu, and if you go down to option number 5 and then type in pi over 4, pi divided by 4, that draws the tangent line, and it also gives you the slope of the tangent, or gives you the equation of the tangent line. So if we look at the bottom of the screen here, we see y is equal to minus 1.9999866666669x plus 1.5 and some change after that. Okay, so this is y equals mx plus b form, mx plus b. The x is obviously the independent variable. This represents the slope, which is an approximation. By the way, do you think the exact slope might be -2? It is. And the y-intercept over there, we don't have the full thing on the screen, but I think if we scroll over, we can see. Maybe we can't. Let's see. I don't know if this calculator will actually give me the entire. Let's see, pi divided by 4. There's the equation. How do I get to? No, that doesn't do it. Well, at any rate, there's a y-intercept up around 1.5. What we're most concerned about is the slope. So the equation of the tangent line. Now, on your exam, you were not allowed to use a calculator, so we had to work through this using the idea of point slope form, y minus y1, m times x minus x1, and I had given you the x1, so y minus y1, x minus pi over 4, that was given in the problem. Okay, to find the y value, you would have to go into here. Y is the cosine of, no, it says 2 times x, so that would be pi over 2. And the cosine of pi over 2 is 0. So now we have y minus 0 is m times x minus pi over 4. Let me get that out of the way. And then lastly, to get the slope, you would need the derivative, and you could get that from here. Y prime is -2 sine of 2x, and y prime at pi over 4, which is where we're trying to calculate the derivative, would be -2 sine of pi over 2, which is -2, right? Because the sine of pi over 2 is 1. Okay, so y is equal to negative 2 times x minus I over 4 was the answer with the equation of the tangent line. Now again, tangent lines are used a lot to approximate functions. And that's what section 3.9 is talking about, using a tangent line approximation. So let me pull up a new page here. Example 1 on page 235. Again, if you have your text, it's on page 235. If you do not have your text at home, go to the topics page and you will see the scanned information from the textbook. It says find the tangent line approximation. Here's your function. F of x is equal to 1 plus the sine of x. And it says at the point 0, 1. Okay, and then it sort of works through that. I think if you want, you can immediately jump to this y minus y1 m times x minus x1 and say, okay, we're given the y coordinate, it happens to be 1. We don't know the slope yet, but we can get to it pretty easily. And we're given the x coordinate, that happens to be 0, right? So the x coordinate and the y coordinate of the point are given. That goes in very quickly. And then you just need to find the slope. So f prime of x, let's see, the derivative of this function. Well, the derivative of 1 is 0, and the derivative of sine is cosine. That's the derivative. But we want the derivative at the point where x, remember x, is equal to 0. So that's the cosine of 0, and the cosine of 0 is 1. So that fits in right here. And now we have the equation of the tangent line. Y minus 1 is 1 times x minus 0. Or if you want, y minus 1 is x. Or even better yet, y is equal to x plus 1. Okay, so this is the equation of the tangent line. Remember, the calculator does this. If you have access to the calculator, access to the technology, you can do this very easily. You type in the equation, which was 1 plus the sine of x. Here it is in the trig window. Zoom 7 is the trig window. Okay, sine wave. And we're trying to draw the tangent line when x was equal to 0. Okay. So there it is, and again, you see the equation of the tangent line on the bottom. Y is equal to 0.999999. Well, that's wrong. It really should be y is equal to 1x plus 1, and that's what we have down here. Okay, so we can get the equation of the tangent line pretty easily. Now, what they want you to do is to look at the functional value and the tangent line at various x values close to 0. And they have a table, and I'm going to create that table on my calculator by going to table setup, and let's see. We will go ahead and just change the independent variable to ask, and then look at the table. So instead of graph, it's going to be second graph. That's the table. And for various x values, negative 0.5 was the first one in the text. You see the y1, that's the functional value, 0.52. Now in the text, they've, what did they do? They rounded that to 0.521. The calculator gives us a more accurate approximation. If we arrow over, you see on the bottom here, the functional value is 0.520, 5744, and you could round that wherever you want to. But the other thing the textbook has is the equation of the line. And we can add that to our table by going and putting in y2 as the equation of our line, tangent line, which is x plus 1. And then when we look at the table, we have not only the functional value, the quote exact value, but also the tangent line value. And you see they're relatively close. Okay, so let's go down and put in another x value, like negative 0.1. And we get the functional value and the line. And we put in negative 0.01, okay, and we get some more. Now again, in the table here, it looks like they're the same value, but if you arrow over, you'll see that's the quote exact value, 0.99000001666666. That's putting that x value into the trig function, and this is putting the x value into the line. And obviously, they're very close, but they are not exact. They're not exactly the same. If we do put in 0 for x, then both the wave and the line are exactly the same value. And that's true because that is the point of tangency. So both the x and the y value, or both the y values for the two, the curve and the line are the same. And then you could do that for the positive values as well. And it says that if you look at points near the point of tangency, the line and the graph are about the same. And if we just go back to the picture and maybe draw, let me zoom box here. Zoom box is one, and you might know how to do zoom box. You just sort of arrow the cursor over, and you place one corner of the box where you want it, let's say right there. And then as I arrow to the right and down, a box is created that's going to the right and then going down. Okay, so I'm just sort of going around our point of tangency here. I'll go back to the left just a bit. And then if I hit enter, I now have a window that shows the curve and the tangent line. And obviously near the point of tangency, they appear about the same. It looks like the sine wave is a straight line. It's not, it's curved, but it's very close to being linear. Okay, so that's example one. There's a note on the bottom of page 235. Be sure you see that the linear approximation depends on the point of tangency. At a different point on the graph, you would obtain a different tangent line approximation. Well, that's sort of obvious, I hope. Now, to show where the differential idea comes in, we're going to introduce one other idea. If we let the function, for this first example, be 1 plus the sine of x, and then we let the line, this tangent line that we got, I'm going to call it L, which is x plus 1. L is equal to x plus 1. Okay. We'll see that the line and the function are close to one another. The line is close to the function, and I'm going to write it this way, that the function, okay, so f of x, which is 1 plus the sine of x, is about the same as the line. And the line in this case was x plus 1. And I'm going to make the note here that this approximation is reasonable if x is close to 0. And we just might want to note 0 is the point of tangency. Okay, so 1 plus the sine of x is about the same as x plus 1. And that's a reasonable statement as long as x is close to 0. Okay. Now, turn the page, 236. When the tangent line to the graph of f is at the point C, f of c, we're going to sort of generalize this idea. So instead of saying, let me just scroll down here. Instead of saying for a particular situation where f is equal to 1 plus the sine of x and L is equal to x plus 1, what I want to do is I want to generalize it. And so we have f of x, we have a point on f, point on the graph of f, and we'll call that c f of c. Okay. And then we need the tangent line to the graph at this point, c f of c. This is our x value, this is our y value. And let's see, what else do we want? Let's go and write down the equation of the tangent line, y minus y1 m times x minus x1. Okay, so sort of think how we did it in a particular case. We put in the y value, that would have been f of c. We put in the x value, and that would have been c, and that's coming from here, right? So c goes there, and f of c goes there. And then we needed the slope. Well, we don't have a particular function. The function was f of x, so the derivative is f prime of x, but we wanted to evaluate that at this particular c value right here, right? So c is going to go right in there. So the slope we needed, slope is going to be f prime of c, and that's going to be a number. In the previous example, it was 1. The one on the exam, it was -2. But that's going to go right there. Okay, so a lot of arrows here. Let's see what we've got. We got y minus f of c is equal to f prime of c times x minus c. And now again, remember, this is one number. That's the slope multiplied by x minus c. So our tangent line now, our line, if we move this across, we can say y is equal to f of c plus f prime of c times x minus c. Okay? And so lastly, here's our approximation, the function, the curvy function. And, just for memory purposes, this may help. When I use a capital L, that's using straight line segments. So that's a line, straight line. And when I draw the F, I'm using curves, right? So it's a curvy F. That's going to be our curve. Okay, so f of x is about the same as L of x. And L of x is f of c plus f prime of c, x minus c. And this approximation is good. F of x is about f of c plus f prime of c, x minus c, for points near x is equal to c. Okay, so for points near x, f is equal to c. Okay, so that's the top of page 236. And then they talk a little bit more about changes in y's and changes in x. And they define what we mean by a differential. And you can look at that on page 236. I want to just mention a couple of things that dy, delta, whenever you see a delta, that's the actual change in y. Delta y is actual change along the curve. And dy is the change along the tangent line. Okay, and because the tangent line is close to the curve, oftentimes these are close to one another. So we see delta y, by definition, the change in the y. So f of c plus delta x, you can refer to the diagram in the text, minus f of c. That's just the change in two y coordinates along the curve. Okay, and that's going to be about the same as dy, and dy is going to be f prime of c times the change in x. So that might be x minus x1, or just whatever change in x there is. And this is along the line. Okay, so this is curve. Change along the curve is about the same as the change along the line. Okay, how to find dy, this approximation dy? Well, dy is simply defined as the derivative times dx. And if you just sort of think like you were an Algebra 1 student, if I told you f prime was given the symbol dy dx, and if you thought of this as a fraction, then it would sort of make sense. You just multiply both sides of the equation by dx, and you get this definition for the differential dy. Okay, let's see. Let's go through example 2. We are not going to do any error propagation in this course, so we don't have to worry about that, although in science class you do that a lot. Let's just do example 1, comparing delta y and dy. Example 1, we have the function x squared, right? F of x, that's the curve, x squared. And we're supposed to find dy, that's the little differential, when x is equal to 1 and dx, the change in x, is 0.01. And by the way, I might want to note another thing here. If you look at the diagram, you'll note that dx and delta x are always the same. So these, in fact, are the same, whereas delta y is the exact change, and that's about the same as dy, right, which is the change along the tangent line. So just be sensitive to that. You can replace delta x with dx, and vice versa. You cannot replace delta y with dy. And maybe, again, a little sketch would help here. If this is our curve and this is our point, here's C and F of C, and here's our tangent line. I'll do that in green. Tangent line in green. If you go a certain distance, C plus delta x, you will get a point on the line, and you'll get a point on the curve. The true change in y would be this distance right here. This is delta x. So this distance here, from here to here, okay, that's the true change, delta y. True change along the curve as the point moves from here running up to there. Okay. Along the tangent line, however, and I'll use green for this, just look at this little triangle. And you know the slope of a line is rise over run. This is going to be dy and dx. So the change in x, this delta x, is this amount here. Change in x from here to here, delta x. Okay, and dx, which is part of this little green triangle, are the same. Those two are the same. But for the change along the tangent line, that's dy, and the change along the curve is delta y. That's this amount way over here. That's delta y. Those are not the same. Although as you get closer and closer to the point of tangency, you know, imagine zooming in here and looking at a little tiny piece down here. This triangle right here, right, has a smaller dx and a smaller dy. And there, the change along the curve is almost the same as the change along the line. Okay, as you get close to the point of tangency. At any rate, let's go ahead and work this example. It says find dy when x is 1. Okay, so the first thing we do is we get dy is f prime of x dx, right? And so the derivative is 2x dx, and we were given that x is 1. So dy evaluated when x is 1 and delta x or dx is 0.01. We can evaluate that. We get 2 times 1 times 0.01, and so we get 2 hundredths, right? 2 over 100, 0.02 if you want. Oops, I guess I should include this fact as well. Okay, so what we did was we found dy as 2x dx, and then when we evaluate it at x is equal to 1 with a delta x of 1/100th, we get 2 100ths. Okay. Error propagation, we'll skip that. So don't worry about example 3. Calculating differentials. Should be fairly straightforward. You can look at example 4. A little bit there on the chain rule, down bottom of page 238. Sort of look and read that. Notation by Leibniz. You see the chain rule down there. We know dy dx. If you have that as dy du, derivative with respect to the inside, you have to multiply that by du dx. A quick example, y is equal to the sine of 2x, as on the exam. And dy dx, well, this is the sine of something ugly. So you take the derivative of the outside with respect to the ugly, that's the cosine of the ugly, leave that alone. Okay, so cosine of 2x, and then multiply that by the derivative of the ugly. In this case, u is 2x. So the derivative of the ugly was 2. Okay, so you already know this. This is the chain rule. It's just being applied to differentials. Okay. Approximating function values. I really like example 7. We're going to work on this in class on Tuesday, assuming we're here Tuesday. And if not, then I'll put together another short little video. It says approximate the square root of 16.5. Okay, so our curve, our function is the square root function. Our tangent line, L. Now, we need a point of tangency, so we're going to have to think, do we know anything about the square root curve? Are there points on the square root curve that we know? And one point that might jump out at you is 16, 4. 16, 4. Why do I choose that one? Well, because I have a x and a y coordinate. I'm trying to find the square root of 16.5. So what I want is this value. It's obviously a little bit more than 4, but how much more than 4? What we're going to do is we're going to run a tangent line. So let's get our tangent line approximation. And again, I don't think we have to do this every time, but let's find equation of tan line to the graph. Y is the square root of x at the point 16, 4. Okay, so we can do that reasonably easily. Y minus y1, m times x minus x1. We plug in all the information. Y minus 4, x minus 16. Now we need the slope, so we need the derivative. The derivative to the square root function is 1 over 2 square roots, but that's not the number we need. We need a number here for slope. So we have to evaluate that at an x value, which is 16. So that's 1 over 2 square roots of 16, which is 1/8. Okay, so my tangent line, y minus 4, is 1/8 times x minus 16. I'll move the 4 over, so I get y is equal to 4 plus 1/8 times x minus 16. That's my line. Okay, and then just note that the function, the curve, the square root of x, is about the same as the line. The square root of x is about the same as the line. And the line is 4 plus 1/8 times x minus 16. Okay. And again, just sort of note that the notation that we had before is going to appear again and again and again and again, especially in second semester calc. Remember, AB doesn't do a lot in second semester, but for the BC class, they spend like 7 weeks on this idea of approximations and series. So the function is about the same as the y value, f of c, plus the slope of the tangent line at c times x minus c. So if we had all those components right up front, we could have written that the square root curve is about the same as the y value, 4. The slope we'd have to calculate, that was 1/8 x minus 16. Okay, so this is our approximation. and this is good for x values near 16, right? Near the point of tangency, near 16. So sure enough, the square root of 16.5 is about 4. Well, we sort of knew that. We knew the square root of 16.5 was about 4, but now we have a little bit more information. 1/8 times 16.5 minus 16. So the square root of 16.5 is about 4 plus, what's this? This is 16.5. Take away 16 is a half. So 1/8 times 1/2. So the square root of 16.5 is about 4 1/16. Okay, just so that we're sort of comparing this with what we know on the calculator. Let's see, 4 plus 1/16 is this decimal, right? 4.0625. If we actually jumped on our calculator and said, what was the square root of 16.5, the best approximation my calculator gives me, I get 4.0620. So we're off by 5/10,000ths, which isn't bad. And the other thing you might want to note is that our approximation here is a little bit too big, which sort of makes sense when you look at the picture again. Okay, so the curve was bending this way, and our tangent line was above the curve. Right, here's our point of tangency. This represents 16 and 4. So as we travel along the line, it makes sense that we're rising faster than we would be if we were traveling along the curve. So the approximation is a little bit too big. Okay, that's all I'm going to do on this video. Work the exercises. The assignment is on your assignment tab. You can look there. I certainly want to work problems like 1, 3, 5. And we'll do more of this on Tuesday. Okay, stop this here.